In this video, we're going to look at compressors and turbines. And now a compressor increases the pressure of the gas stream and causes the gas to be sort of pumped. Now, compressors, of course, require work. And actually, they require power, to be more specific. And turbines, they use steam to produce power. Now, they can use other gases. It doesn't have to be steam, but it's usually steam, and they use steam to produce power. And and so they expand. So the gas, the opposite of being compressed, the gas expands as it goes through a turbine. Now let's apply this to our one inlet, one outlet equation of the first law. So remember, we had heat, rate of heat transfer minus work times this equation. Now, we're going to assume for both compressors and turbines, we're going to assume that this change in kinetic energy is zero. That's a normal assumption you can make when dealing with compressors or turbines. And then over here, we're also going to assume there's little or no change in the elevation. That's almost for sure. So that the change in potential energy is going to be zero. So you can see that now what you're left with is rate of heat transfer minus the rate of work done is going to be equal to the mass flow rate times the enthalpy out minus the enthalpy in. And a couple things to remember when we're doing problems in this section. The mass flow rate is equal to the volumetric flow rate divided by the specific volume. Remember, the specific volume is 1 over the density. And of course, the volumetric flow rate, that's usually going to be maybe meters cubed per second or meters cubed per minute. Uh, and then the specific volume, of course, is meters cubed divided by, say, kilogram. And so you can see the meters cubed will cancel, so we'll have kilograms per minute or possibly kilograms per second. And of course, in English units, this could be feet cubed per minute or feet cubed per second. And this is going to be feet cubed per pound. And also recall that power is the rate of doing work. And adiabatic means no heat transfer. Let's take a look at this problem. Refrigerant 134A enters a compressor at 100 kPa and minus 24 degrees Celsius with a flow rate of 1.35 meters cubed per minute and leaves at 800 kPa and 60 degrees Celsius. Determine the mass flow rate of the 134A and the power input to the compressor. So let's take a look at this. We have a picture something like this. This is our compressor, and this will be our control volume, or our system is with what is within the dotted lines. And now we are not told anything about heat transfer, so we can assume it's adiabatic. Which is a reasonable assumption. Again, though for compressors, it's not necessarily going to always be adiabatic, but I think in this case, since we're not given a lot of information, we can assume that. So it's going to be insulated. So puts the things right there to show it's insulated. And so let's go ahead and we'll apply our equations. So I guess first we need to find the inlet and outlet properties. So let's take a look at that. So our inlet conditions are 100 kPa and minus 24 C, outlet 800 kPa and 60 degrees C. And we'll have to check to see what conditions these are. So for 134A, if we look up 0.1, so we have 100 kPa, which is 0.1 MPa. You can see the saturation temperature is minus 26, and we're actually at minus 24. And believe it or not, that would be considered superheated because we're above the saturation temperature for that pressure. So we have to go to the set superheated tables. And so if we look over here at the superheated tables for, again, for 0.1 and minus 24. And so actually you can see that's going to be between minus 20 and minus 26. And that's going to be, now I interpolated this and I got 0.1947 for the volume. So let me actually note this here. And I should say that's a specific volume. And again, you can double check my interpolation. So I'd be interpolating between -26 and -20. And you can see I got something sort of between those two values. And then for the enthalpy, uh, when I interpolated here, I got uh, around 230. And for the enthalpy, when I interpolated, I got about 233.3 kilojoules per kilogram. You can double check it, especially this one. I'm not sure if that's exactly right, but definitely very, very close. Then now over here, we'll check this as well. So at 800 kPa, we're at 60 degrees. And that'd be 0.8. And the saturation temperature is 31.33, so we're also superheated. Again, if we look at the superheated table at 0.8 MPa, 60 degrees, fortunately, this time we do not have to interpolate since we have 60 degrees right there. And this, you can't see the top of here, this is the specific volume is 0.02992, and the over here is the enthalpy. It's 294.98. And now we're going to need the mass flow rate. And remember, the mass flow rate is going to be the volumetric flow rate divided by the specific volume. And we're told that for the inlet, we have 135 meters cubed per minute. And then we have 1947 meters cubed per kilogram. Now, of course, be sure that you're using the inlet conditions because this was the inlet volumetric flow. And so don't use this specific volume, use this one because we want the one associated with the inlet flow rate. By the way, there is a decimal point there. And so when you put this in your calculator, you get 6.934 kilograms per minute. And we said we're going to ignore change in potential. Excuse me, we said we're going to ignore changes in potential and kinetic energy. So those terms go away. And also we're assuming it's adiabatic. And so we're going to end up with negative work times the mass flow rate. And we're going to have H2 minus H1. And when I put this in my calculator, I get 427.7 kilojoules per minute. And now, if we divide this by 60, that'll give us kilowatts. So let me do that. And it's about 7.13 kilowatts. And it's negative, which indicates it's work done on the system. And the system would be the gas itself, or in this case, the R134A, like this. Next, let's take a look at this problem. Steam flows steadily through an adiabatic turbine. The inlet conditions of the steam are 6 MPa, 400 degrees Celsius, and 80 meters per second. And the exit conditions are 40 kPa, 92% quality, and 50 meters per second. The mass flow rate of the steam is 20 kilograms per second. We're going to find the change in kinetic energy. Now that's going to be in kilojoules per kilogram. Kilojoules per kilogram. We're going to find the power output and the turbine inlet area. I want to find these things. So we have a picture something like this. And we can assume that our system is adiabatic, no heat transfer, so we could actually show it is insulated around here. Like this. And we can also assume there's no change in potential energy. And that's pretty clear cut because there's not much of a change in elevation anywhere through this. So let's take a look at the conditions. The inlet conditions are this, and the outlet conditions. This is a saturated mixture because we're given a quality. And that's kind of indicated, by the fact that, so we're probably on a TS diagram, for example, we're probably like about out here at 92%. And if we look up these values in our table, we find, so we look in the steam table, remember, be sure to look up steam. we can see that at 6 MPa, the saturation temperature is 275 degrees, but our temperature is 400 degrees Celsius. So that means we're going to be superheated. So if we look up at 6 MPa, at 400 degrees, we're going to find that our V, our specific volume, is 0.04739, and our enthalpy is 3177.2. Again, depending on which table you use, these values could be slightly different. I know I have two different books, so uh, and they don't show the exact same values for these. So if it's a little bit off, that's not a problem. Now for the outlet, we know because we're given a quality, we already know it's a saturated mixture. And so since we're saturated uh, at 40 kPa, we use this value for VF, this value for VG, and of course put everything into this equation here. So we come up with 3.67 meters cubed per kilogram. So let's do the same thing for H2. Now for H2, for the enthalpy, we don't have to actually do the subtraction up here because at least my table has that done for us. So when we do this, I can just use this HFG. And again, if we look that up in our table for 40 kPa, those values will be 317.58, and that difference is 2319.2. And so when we substitute our values, we get this. And I get 2451 kilojoules per kilogram. Once again, depending on what table you're using, these values could be slightly different. So if you're finding that, it's not a problem. So let's actually calculate some of the things that we were asked to do. Now, the easiest one, the change in kinetic energy, is going to be very easy because we're given the inlet and exit velocities. So we can just calculate for A, change in kinetic energy is going to be V1, excuse me, V2 squared minus V1 squared divided by 2. And this is going to give us a 1950 meters squared per second squared. Now, we would eventually like to get this into kilojoules per kilogram. So notice that, let me just rate this here, 1950. If we multiply this by kilograms over kilograms, then we can separate this out. And then we can change that kilogram meters per second squared. and we're left with a meter and a kilogram. And of course, this is a Newton. And so Newton meter over kilogram, and that's actually a joule per kilogram, like this. And actually, I noticed I forgot the negative sign. When we do this, this would be negative here. Please fix that. So we have something like this. Or finally, if you want to change it to kilojoules, this is going to be negative 1.95 kilojoules per kilogram, like this. So that's going to be the change in kinetic energy. That's going to be the change in kinetic energy. I should say uh, the kinetic energy per kilogram. So that's for part A. Then for part B, and I said we're ignoring change in potential energy. So we can put this into here. Then we can substitute the values that we've found so far. We're assuming it's adiabatic, so this is going to be 0. And we're given the mass flow rate, 20 kilograms per second. And we're given the H1, well, we calculate the H1, the H2. And then we'll subtract our kinetic energy. And this is going to be negative on the right. It'll be negative 14,559. But then we multiply this negative, it's going to be 14,559. And the kilograms cancel, and it's going to be kilojoules per second. And that is actually a kilowatt. Again, you may have got some different numbers because your table is a little bit different, but it should be around 14,500 to 15,000, somewhere in that range. And finally, the turbine inlet area. And we can use this to calculate that. We know the mass flow rate. We can find the density from the uh, specific volume. And let me actually write that down just to be clear to everybody. So we can remember density is one of the specific volume. So now let's solve For this here, let me solve for A1. Again, the small v is specific volume. And let's substitute our values. And we substitute our values. These were given 20 kilogram per second was our mass flow rate. The specific volume, we found that to be 04739. And of course, that would be meters cubed per kilogram. And divided by the inlet velocity, which is 80 meters per second. And so our area is going to be 0.1185. And let's check our units. Kilograms will cancel. The seconds will cancel. And this would be meter cubed divided by meters. So it'd be meters squared. So that's going to be our inlet area. Next, let's take a look at this problem. Steam flows steadily through an adiabatic turbine. The inlet conditions of the steam are 8 MPa and 400 degrees Celsius. The exit conditions are 100 kPa with a quality of 95%. The mass flow rate of the steam is 30 kilograms per second. Determine the power output. And then part B is if the inlet velocity and outlet velocities are to be 15 meters per second and 10 meters per second respectively, what inlet and outlet pipe diameters are required? So let's take a look at this problem. Again, the inlet temperature is 40 degrees Celsius, pressure 8 MPa, flow rate of 30 kilograms per second, outlet 100 kPa, and the quality of the outlet is 0.95. And if you're doing these problems, keep in mind the equations you want to solve. You have Q dot minus W dot is M dot times the change in enthalpy, change in kinetic energy, change in potential energy. Now, for a turbine, there's no elevation change, at least not a significant one. And if we're not given enough information to calculate the velocities, we can assume there's negligible change in kinetic energy. So for this case, we can assume the change in kinetic energy, change in potential energy, both zero. So these will go away. And we know the mass flow rate. And we can also assume it's adiabatic. And actually, in this, looking back at the problem, actually, it tells us it's adiabatic. So this goes away. So the problem actually becomes pretty simple. We just have to apply this. So we just have to look at the inlet conditions and the outlet conditions. The inlet conditions are 400 degrees C and 8 MPa. So let's put those down here. The fact that they've given both of these tests means they're probably superheated, but we'll check the table in a minute just to be sure. And the outlet is obviously that's going to be a saturated mixture. Pressure is going to be 100 kPa, and the quality is going to be 0.95. So again, let's look at our table. Again, you could go maybe just directly to the superheated table and see if you could find these, though the probably the more direct way to do it is to start with the saturated table, the saturated steam water table, and go from there. And so if you look up, this is in my book, it's A11. So the saturated table at 8 MPa, our inlet, the saturation temperature is 295 at 8 MPa, but we're hotter than that. It's our temperature is above that. It's 400. So our temperature is above the saturation temperature. So that means it must be superheated. And so let's go to that table. In my book, that's table A12. So for 8 MPa over here and 400 degrees C, uh, we're going to be along this row here. And we're going to need this volume and this enthalpy. So let's write those values down. 0.03432 and 3138.3. So write those values down here, and then once we have those, we want to look over here at the outlet. And obviously for this one, we know it's a saturated mixture. And so we're going to have to apply, uh, our equation. It's going to be V1, of course, it's going to be VF plus X times VG minus VF, like this. Same with, excuse me, now be V2, and then H2 is going to be HF plus X times HG minus HF. So we'll look up our values in our table. Again, we're at 100 kPa. So we're looking at our table over here. Get under kPa, only goes to 75, but over here, MPa, it'd be 0.100 MPa. So we're going to look along this row, and we're going to need our values of VF, we're going to need VG, we're going to need HF, and actually they give us, for the enthalpy, they give us the difference between HF and HG right here, so we don't have to calculate that difference. So we'll write down those four values. So I went ahead and wrote down the VF, VG minus VF, and calculated our V2, and then put in our HF and HG minus HF. As I mentioned, my table has that difference calculated for me, and found H2. So now we can do the rest of the problem. So just going to apply what we found a minute ago here. And so this is going to be, let's see, our flow rate was 30 kilograms per second. Our delta H, of course, is going to be there, H2 minus our H1. Like this. And when you put these into your calculator, you get negative 17,272. But then we multiply by this negative that becomes a positive. And it's going to be the kilograms are canceling. So that's kilojoules per second. Or that's 17,272.2 kilowatts. Remember, a watt is a joule per second, so kilojoule per second is a kilowatt. So that's the answer for the first part. Now for the next part, we have to find out the diameters of the inlet and outlet. And so for part B, and we're told the velocity of the inlet, I'll call it velocity 1, is supposed to be 15 meters per second. And so we know to calculate this, we're going to need to use m dot equals rho 1 A1 V1 for the inlet. And let's actually solve this for A1. So A1 is going to be equal to m dot divided by rho 1 V1, like that. And now, of course, Rho 1 is 1 over V1, and we calculate V1 back here. So we could actually write this as A1 is equal to V1 m dot divided by velocity 1. Of course, the small v is the specific volume. So let's go ahead and put those values in. And our specific volume is 0.03432 meters cubed per kilogram and 30 kilograms per second, and divided by the velocity we want to maintain is 15 meters per second. When I put this in my calculator, I got 0.06864, and let's check the units. Kilograms will cancel. Let's see this when we do the reciprocal, the seconds will cancel. And then meters cubed over meters, so it's going to give us meters squared, which we would expect for area. Of course, to find the diameter, we would use this equation. Do the square root. It end up being A1 divided by 0.25 pi, like this. And D1 is going to be the square root 0.6864 meters squared 0.25 pi, like this. When I put this in my calculator, I got point 0, yeah, excuse me, 0.296. So it'd be approximately zero point 0.3 meters. So that's going to be our inlet diameter. And then for the next part, similar idea. For the outlet, we're going to have V2. It's supposed to be 10 meters per second. And we'll use the same equations that we came up with here. We're going to say our A2 then is going to be specific volume times our mass flow rate divided by our inlet velocity. And so for, except these are all going to be 2's now. Of course, the mass flow rate's the same all the way through, so we can just call it m dot. And over here, we got for our V2, we found that to be 1.619. And of course, our mass flow rate's still the same, 30, what was that, 30 kilograms per second. And we're supposed to keep our exit velocity at 10 meters per second. And if you put that in your calculator, I get that the area should be 4.857. meters squared. Again, check the units. Kilograms cancel, seconds cancel, meters squared. Then finally, our diameter, 2.49 meters. This. Again, that's the outlet diameter. And it's not surprising it's larger because our specific volume is much bigger this time because the gas has expanded quite a bit.